Here, we're going to focus on the example from the book and other examples as well to check out how we actually do this hypothesis test or the t-test of two means. So we have here sample data of mothers with newborns. And if I remember correctly from the textbook, there are, I think, 150, n equals 150. And here we just have the first four cases from this data set and see births. So this is the data set of mothers with newborns. So the unit is a person, a mother. And there's all kinds of information about them, how many visits they had, marital status, weight of the newborn that they had, the gender of the newborn, so on. Of course, to know what all these variables means, you have to check the details of the data set. The idea here, though, is that we want to know if there is convincing evidence that statistically convincing evidence that newborns from mothers who smoke have a different average birth weight than newborns from mothers who do not smoke. Okay, so we see the two groups here: mothers who smoke versus mothers who do not smoke, and we have a habit variable that identifies there. Now here we only see non-smoker, but we assume that there are also some data in the data set where the habit is smoker. And as I'm going to emphasize too, we only focused on two groups at a time, because this is a two sample t-test and it has to be just between two groups. And then what we're checking is the birth weight, or the average birth weight. So in this case, let me ask you a question. What would be the explanatory and outcome variables in this study? Pause the video now and think a little bit. Well, I think very clearly the explanatory variable, that is the causal variable, is here called habit, or it's called smoking habit. And the outcome variable is birth weight, right? Weight or birth weight. Now, because if we're only doing a t-test, we cannot actually really get this causal linkage established. What we're only doing is looking at the association and the statistical probability of the association. For us to actually establish the causal relationship, we would need a controlled experiment. So if we continue with this study here, this idea, one of the first things we do is set up the hypothesis, the null hypothesis, the alternative hypothesis. And here we're using the mu symbol rather than the X bar, because we want to know what would happen in the population, right? So we're making an inference not just from the sample, but we want to know in the population in general, assuming a normal distribution and given the other statistical considerations we have done. So we set up the null hypothesis that the difference between non-smokers versus smokers equals 0. So that's the null. We assume that there is no difference between them. And alternative hypothesis that no, the difference between this is the average birth weight from non-smoker mothers and the smoking mothers, it is different than 0. So there is a difference between them. This may seem like the previous difference of the paired means, but just remember that we have to understand our data set and whether or not we're dealing with paired means or unpaired means. And it should be relatively easy to tell because, for example, in this data set, a mother is a smoker or a non-smoker. So it's not paired because they're not two variables of the same individual. One mother is a non-smoker, another mother is a non-smoker, and maybe there's another mother here who is a smoker. So that is unpaired means. As usual, we need to check the assumptions. So because the data come from a simple random sample of mothers, the observations are independent, both within and between samples, meaning, well, they already told us that this was a simple random sample of mothers, so we can believe them. And because it is a simple random sample, every individual person was randomly selected in the data set, and it is um, the, the data, the observations are independent within this, with the whole sample, then we can assume that it's, if we separate the data, if we separate the data, the mothers who smoke and mothers who don't smoke, then we can assume that it is also randomly sampled or independent between these two. Um, Here we also do a histogram of the data uh, for both, separated for mothers who smoke. The bottom panel represents the birth rates for infants whose mothers did not smoke, mothers who did not smoke, and mothers who did smoke. So they're both uh, bell-shaped curves, so they kind of look normal. And also we have over 30 observations for each, so that also gives a sense of normality. And then I'll show you also how to check that mathematically with a R function. So because since we're working with a single data set, we will want to separate the data for smokers from non-smokers. And we can do that very simply with an R subset function. So you can create a smokers data set and use the subset function with two inputs. The first is the data, whatever the data is. So this is the data frame. And then there's another parameter for identifying the condition or the filtering column. So this is the habit. Habit is the habit column here from the data set. And make sure that when you have this condition testing, this is kind of testing a condition. This is kind of like an if statement. We need to put the double equals. So not the assignment equal. It's a different kind of equal here. This the double equal is a testing a condition, where the single equal is usually an assignment. You're giving the one value on the right to the thing on the left. This is not the same. This is a check. And because the data type is categorical or is a text, we need the quotes. If it's non-text, if it's number, it goes without quotes. So if we had, for example, 1 for smoker, 0 for non-smoker, we wouldn't use these quotes. So we create a data frame of just smokers, a subset of that data frame, and a data frame for non-smokers. Another step, following step, is determining the confidence level that we're going to use for our hypothesis test. And generally it is 95% or point. Often we actually talk about this in the how we will compare to the p-value. So it's 0.05, which is the other end of 94%. If we want to avoid rejecting the null hypothesis incorrectly, now let's note this. If we want to avoid rejecting the null hypothesis incorrectly, that is, if we want to be more conservative and make it difficult to reject the null hypothesis, we may raise our confidence level to 99%, so that we would have to compare our p-value with 0.01, means we would want our p-value to be less than 0.01 to reject. And if we go with 95, we would want our p-value to be 0.05 or less to reject. Raising the confidence level reduces the chance of a type 1 error, which is to assume that the null hypothesis, to reject, reduce the chance of rejecting the null hypothesis when it is in fact correct. And following that, we calculate the t-score as we have done before. So the t-score for comparing two means is similar but not identical to the previous t-score calculations. Recall that the t-score gives us the standard deviations from the mean in a distribution, and it enables us to find the probability of getting that t-score. So we're dealing with some kind of numbers when we're dealing with average weights. Maybe it's in pounds or in kilos, maybe it's 6, maybe it's 7, maybe it's 10. But when we get the t-score, we put it in terms of standard deviations from whatever the mean is for that thing. And we to actually so this equation here gives us the t-score first, which is the place on the distribution. Okay, it's the number of standard deviations from the mean of whatever variable and data you are working with. In this case here, it's 1.54. So 1.54 means we are 1.54 standard deviations from the mean. But that's not enough to give us the probability. For us to understand the probability of getting this value, we need to put it into a kind of probability function like the PT function of R. And the PT function of R, we give the t-score. That's the first parameter, t-score. And we also need to give the degrees of freedom. So there's a calculation here for the degrees of freedom. So it's the minimum of the n for the one sample minus one, or the n, the other sample minus one. So you choose the minimum of the two. Okay. So in our case here, on when we divided the previous data, we had, we said the n was 150, and I think it was 100 for one and 50 for the others, 100 non-smoker and 50 smokers. So we'll take the smaller one minus one, which is 49. And there's a little bit of a tricky thing here when we use this probability function, and that is it counts from the left. So if we are using a positive, if we're using a positive t-score, which is going this way, we may want to, there's different ways to go about it, but we want to include this the lower tail parameter as false. And that gives us a p-value that we already work with directly. The other approach would be to minus whatever result we have from one, subtract whatever result we have from one. But because we changed this parameter to false, the result we get is the p-value. So that's what the PT function gives. It always gives us the p-value, the probability value of this t-score, given a particular degrees of freedom. And just remember that trick. If we have a positive t-score, you want to make sure that the lower dot tail parameter equals false. But because we're also doing a two-sided test, so this gives us a one-sided test. That is, there's a 6.5%, 0.065, or 6.5% chance of getting this value, which is kind of high. It's higher than 0.05. But we also doing a two-sided test. This is only a one-sided test. This only gives us a one-sided test. So we need to multiply this number by 2, which increases it even more, right, to 1.3 or something like that. And that's definitely much lower than 0.05. I mean, much higher than 0.05. This is higher than 0.05, and therefore we fail to reject the null. Remember, we want a very low p-value, lower than our confidence level, to reject the null. So we fail to reject the null, and we cannot see in this data set that the difference between non-smoking and smoking mothers is different than 0. That's what we're observing here. The PT function gives us one tail probability, and from the lower tail, which means that if we have a positive t-score, we need to false this lower tail parameter. So just put this in writing here for you that I just explained. Next, we'll kind of expand this to actually doing the t-test directly, which facilitates the calculations, and I will also introduce some new concepts.